In this lesson, we're looking at reviewing complex numbers. So we'll start by looking at the complex number a plus bi. We'll look at adding, subtracting complex numbers, multiplying by scalars, and then multiplying complex numbers. We'll look at powers and expansion, and then we'll look at the complex plane. After we've gone through a little bit of review, we'll look at a couple of examples. Okay, so a complex number is usually referred to as z. So z is equal to a plus bi, where a is a real component of z, so it's a real number, and the imaginary component of a complex number is b. Now, I'm hoping that you can recall that I is the square root of -1, which is our complex number. So complex numbers always come in this form. When we're in component form, that a plus bi, there is also polar form that we'll review in a later lesson. We should know the pattern for the powers of I, so hopefully we can see that I in itself is just square root of -1, so I is I to the power of 2 becomes I squared. Now, what that is square root of -1 squared, which means it's just -1. I cubed is I squared times I, which will be -1 multiplied by I, and obviously that will be -I. I to the power of 4 is I cubed multiplied by I, and so that will be -I multiplied by I, and that will be negative square root of -1 squared. -1 gives us +1. And so this is going to be our pattern, because when we say I to the power of 5, we're looking at I to the power of 4 times I, and that's the same as saying 1 times I, or I, and then the pattern starts again. So what we have is I is I to the power of 2 is -1, I cubed is -I, and I to the power of 4 is 1. Now once we get I to the power of 5, we go back up and we repeat that pattern. Okay, so that's our review on the complex numbers and the powers of I. We're now going to look at adding and subtracting. The most important thing to remember with adding and subtracting is that we keep the real and imaginary components separate. So if we have, looking at addition, if we have a plus bi, and we're adding it to a secondary complex number, which is c plus di, then we'll end up with, in the real, a plus c. Then the imaginary component, we have b plus di. Okay, so the whole process is that we add real to real and imaginary to imaginary, and we keep the two components separate. When we look at subtraction, we take the same approach. We have a plus bi subtract c plus di, and so that means we have a subtract c in the real and b subtract d in the imaginary. Adding and subtracting will be relatively straightforward, and we'll look at a few examples of that shortly. Multiplying by scalars is again very simple, and it's just going to be an expansion. So if we have n multiplied by a plus bi, the n being a scalar value, we'll end up with na and nbi. So that value is just multiplied by each of the individual complex number components. When we look at multiplying complex numbers, the nice thing about complex numbers is it doesn't matter how you multiply them. So let's say we've got a plus bi multiplied by c plus di, so we've got the product of two complex numbers. The outcome will always be a complex number in its simplest form. So this one is one I want to look at an example right now. Let's say we have 3i multiplied by 2 plus 2i. When we expand this out, we have 3i by 2, which is 6i, and 3i by 2i, which is 6i squared. I squared is equal to -1, and we end up with 6i take 6. So it doesn't matter that we've multiplied this and expanded it out, it still ends up in that form, -6 plus 6i, a plus bi. It doesn't matter what power we raise it to. It doesn't matter the values of the multiplication. The outcome will always come back to this a plus bi form. So we can also say that a plus bi to the power of n will always end up in that simple complex number form. Alright, so finally then we'll look at the Argand diagram. An Argand diagram is really just looking at a complex plane. So in a complex plane, it has two dimensions, and we're looking at the real, and sometimes we can call that the x, and the imaginary that relates to the y. So any complex number, let's say z1 is equal to a plus bi, we'll have a displacement in the real direction, a displacement in the imaginary direction, which gives us our complex number. We tend to draw them as vectors even though they're not vectors. We're just looking at the point there. So that is our complex number a plus bi on an Argand diagram or on a complex plane. So that covers a review. That's a bit of a quick run through the skills that we should be able to carry through from the Unit 2 complex numbers topic. And now we'll look through a number of examples. Okay, so all these examples are straight from the textbook. We've got the complex number z is equal to 4 take 5i, and we're trying to find the real component of z. So the real component of z means we're just looking at the real part of this 4 take 5i. Now obviously in this case it's just 4. When we look at the imaginary part of z, we're looking at this negative 5. So negative 5 is the imaginary part of z. Now when we look at C and we go real, subtract the imaginary, we're looking at 4 subtract negative 5, or 4 plus 5, which is 9. Okay, so it's as straightforward as that. If we need to pull out the real and imaginary components, we're just looking at either the real value or the value of the imaginary number. Okay, so when we look at this second example from the textbook, it's saying represents square root of negative 5 as an imaginary number. Now if we apply our third skills here, we can say square root of negative 5 can be broken down into square root of negative 1 and square root of 5. Now square root of negative 1 is I, square root of 5 stays at square root of 5, and we end up with an imaginary number of root 5i. When we look at the second one, where we have 2 square root of negative 9 plus 4i, and we need to simplify this, we can say that's 2 square root of 9 and square root of negative 1 and 4i. So this is 2 by 3i and 4i. So 6i plus 4i, which leaves us with 10i. So again, nice and simple, but a skill we want to practice. When we look at our next example, we're looking to solve the equation 2a take 3 plus 2bi is equal to 5 plus 6i for a and for b, where a and b are elements of a set of real numbers. So what we're looking at is this skill that we've talked about previously, compartmentalizing. So we're looking to be able to equate the real with real and the imaginary. We say let's equate the real. We can say that 2a take 3 is going to be equal to 5. Now what we need to do from there is rearrange and isolate for a. So add 3 and we get 2a is equal to 8. Divide by 2 and we get a is equal to 4. When we equate the imaginary side, we can see that 2b is equal to 6. We don't have to put the imaginary number in there, so it's on both sides, and we end up with b is equal to 3. So in this case, it's really nice and simple. As long as we compartmentalize, we equate the real with the real, and we equate the imaginary with the imaginary. Okay, so when we look at this next example, we've got z1 is 2 take 3i, and z2 is 1 plus 4i. Now part A is simply saying, what's the sum of z1 and z2? So that means we have 2 take 3i, and we're adding on 1 plus 4i. So we're looking to equate real with real and imaginary with imaginary. So in the real section, we've got 2 plus I, and in the imaginary, we've got negative 3i plus 4i. So we end up with 3, and negative 3 plus 4 is 1, so plus I. Okay, it's as simple as that. Part B, we're looking at Z1 subtract Z2. So we have to take 3I, subtract 1 plus 4I. And so if we expand this out, that second bracket with a negative, we have 2 take 3I, subtract 1, subtract 4I. And when we combine the real with real and imaginary with imaginary, we get 2 subtract 1 and negative 3I plus negative 4I. And so we have 1 and negative 7I, or you could just write that as 1 subtract 7I. Now when we look at C, we have 3 lots of Z1, subtract 2 lots of Z2. And so that means we've got 3 lots of 2 take 3I, subtract 2 lots of 1 plus 4I. So we have to expand now using these scalar multiples. So we have 6 and subtract 9I, and subtract 2 and subtract 8I. So the real components will be 6 and negative 2, and in imaginary we have negative 9 and negative 8. And now we have 4 in the real, and in the imaginary we have negative 17. So that can be 4 subtract 17I. Okay, so in this example we're looking to represent the following complex numbers as points on an Argand diagram. So if I draw one plane, then I can put each of these on. So this first one, 2, is just 2 in the real direction. So here's our value of 2. And so as a coordinate, it would be 2 in the real and 0 in the imaginary. And so we can represent it using a line. And there we have, on the Argand diagram, 2. Now we look at B, is negative 3I, which means we're just going in the imaginary direction. So it means we've got 0 in the real and negative 3 in the imaginary. So if we draw our line here, this one's A, which is equal to 2. This one's B, which is equal to negative 3I. Now C is 2 subtract I. So that means 2 in the real and negative 1 in the imaginary. So our point here will be 2 and negative 1. And there's our line, there's our C, is 2 subtract I. When we look at D, we've got negative 2 plus 3I, which D can be rewritten as negative 2 subtract 3I. So that means we have negative 2 in the real and negative 3 in the imaginary. So negative 2, negative 3 is a coordinate. And here we have D is equal to negative 2 plus 3I. Finally, E is negative 1 plus 2I. So it means we have negative 1 in the real and 2 in the imaginary. And so that means our E is equal to negative 1 plus 2I. Okay. Drawing complex numbers on an Argand plane is as simple as that. Okay, so when we're looking at example 6, we're looking to represent the complex numbers Z1, Z2, Z1 plus Z2, and Z1 minus Z2 on the Argand diagram. So if we're going to do this all on one plane, I'll draw a nice big plane. We have real and imaginary. Z1 is simply 2 plus I. So that means 2 in the real and 1 in the imaginary. So here we have 2 and 1. And that is Z1. Now Z2 is negative 1 plus 3 in the imaginary. So that's negative 1 in real, 3 in the imaginary. And so we end up with that point negative 1 and 3. Now we need to look at Z1 plus Z2. So Z1, and if we add Z2 onto it to detail like we would a vector, so that means we're going 1 back and 3 up, takes us up to 1, 4. So this represents Z2. Now, if I choose a different color here and I go red, this line from the origin up to this point here is going to be our Z1 plus Z2. Now with Z1 subtract Z2, So z1 subtract z2. It's the same as saying z1 plus negative z2. Now, negative z2 is just the opposite direction of z2, or we'll be looking at 2 plus I and negative 1 plus 3i. So that means we'll be looking at 2 plus I as our first one, and then 1 take 3i. So if we were to draw this in black, 1 across and 3 down, we can see that it's the exact opposite direction of z2, so this is negative z2. And so now if we draw this one in green, this is z1 subtract z2. Remember, the goal is the ultimate outcome, so we have 2 plus 1 gives us 3, and 1 subtract 3 is negative 2. So if we're trying to show that geometric interpretation of the sum and difference, this is the way we do it, using those vectors tip to tail. Okay, so now if we look at an example with some expansion of brackets or powers, including I, if we're looking at 2 plus 3i and 1 take 5i, we're just going to expand this, so it's going to be 2 multiplied by 1 and 2 multiplied by negative 5i. So we have 2 subtract 10i. We have 3 multiplied by 1 and 3 multiplied by negative 5i, which gives us plus 3i, and then subtract 15i squared. Now we know that I squared is actually equal to negative 1, so we can cancel that and make this positive. We end up with 17 and subtract 7i. When we look at B, we have 3i and then 5 take 2i. When we expand that, we have 3i by 5, which is 15i, and 3i by negative 2i, which is negative 6i squared. I squared is the same as multiplying by negative 1, so we have add 6. So we end up with 6 plus 15i. Finally, C, I cubed. We know straight away that that's going to be negative I. No calculations needed there unless you want to step it out. If we want to look at a larger, more complex expansion, we could look at something like this: 2 plus 3i to the power of 4 and 1 plus I to the power of 3. Now, if we go back and we understand Pascal's enough, we know that when we expand a binomial to the power of 4, we're going to have the coefficients 1, 4, 6, 4, 1. And so we're looking at 1 multiplied by 2 to the power of 4, and then 4 multiplied by 2 to the power of 3, and 3i to the power of 1. We have 6 multiplied by 2 squared, and 3i all squared. We have 4 multiplied by 2 to the power of 1, and 3i to the power of 3. And then finally we have 1 multiplied by 3i to the power of 4. Now when we expand 1 plus I to the power of 3, the coefficients are 1, 3, 3, and 1. So we have 1 times 1 to the power of 3. We have 3 times 1 squared times I. We have 3 times 1 times I squared. And then we have 1i cubed. When these simplify down, 2 to the power of 4 is 16. 4 times 8 will be 32. 32 times 3 is 96i. We have 6 by 4 by 9. So 6 by 4 is 24. 24 by 9 is 2 times 108, which is 216. And the important thing here is we've got I squared. Now I squared means that we're actually going to have a negative 1. We have 4 times 2 times 27. So 27 times 4 is 108. 108 multiplied by 2 is 216. Now it's I cubed. I cubed is the same as negative I. And then we have 3 to the power of 4, which is 81. I to the power of 4, I to the power of 4 is just 1. Now in the second part, we've got 1, 3 times 1i, which gives us 3i. We have 3 times 1i squared, so 3i squared, where I squared is -1. And then we end up with I cubed, and I cubed is the same as having -i. So it simplifies down 16, 96i, take 216, subtract 216i, plus 81, plus 1, plus 3i, take 3, and take I. So if we look at all the real numbers together, we got 16, subtract 216, add 81, add 1, and subtract 3. So -200, -119, -118, -121 in the real. And when we look at the imaginary, we have 96, subtract 216, plus 3, take 1, all in the I. There's 99, 98, subtract 216, which gives us 118, -118. There we have it. We can see that it doesn't matter which power we raise it to, we always end up in that form, a plus bi. Okay, that concludes our lesson reviewing complex numbers and complex number skills. Make sure you practice these skills and build fluency, because they'll be the basis of everything that we do when working in component form in complex numbers.